Now that we know equilibrium and what it is, we want to practice being able to find and use our equilibrium. Doing this, we're going to be looking for what's called a capital K, or the equilibrium constant. And this is the value that's going to show us where we are based on our reaction when we reach equilibrium. To show this, we take a look at this value. If you look on this line, if we're way down here, we're at 100% reactants. Usually this is the beginning of our reaction. And at the end, we'd be at 100% product if we went to completion. Now we know we're going to be somewhere in between, so using the K, we try to determine where that is. If we're at the 50-50, where they are equal, K will be equal to 1. If we're taking a look and we're at reactants, or there are more reactants at least, K is less than 1. And if we're looking and we're higher than 1, that means we have more product. The way to do this is we use something called a K expression. Since every reaction will have its own reactants and products, we have to find this formula. We're going to use products over the reactants as our basic setup. Now, using our generic formula, we're going to take our C's, A's, B's, D's, and we're going to put them into our K expression. Since C and D are both products, they'll be on top. A and B as reactants will be on the bottom. The little coefficients that we have will become the powers. So we'll square or cube or raise something to the 4th power when we're taking a look at the math involved in this expression. So the overall expression for this reaction would look something like this one. Now we're going to go ahead and use a couple of different reactions and try to find these expressions. I want to start off first with the Haber process. That's our N2 plus H2 to get the NH3, or the ammonia. Taking a look here, ammonia is one of the products, so it is going to go on the top. So we're going to go ahead and write it in here. And since we have the 2 over here, we're going to use that as our power. We're going to raise it to the 2nd. So that's only product. So underneath, our nitrogen gas that we have is going to go here. Its coefficient is 1, so it's raised to the 1st. And then we're going to have our hydrogen right beside it. And it will be raised to the 3rd since it has a coefficient of 3. That is the final expression to be able to determine the equilibrium. Now, the second one I want to look at is what we classify as a KW. The reason is because this is for water. Now, looking at this, we have a slight issue. We have a liquid. Liquids are classified as being a pure substance, which means we don't need to use it. So instead of putting it into my K value, we are going to simply cross it off and not use it. Instead, we're going to use that hydrogen ion and the hydroxide ion in our expression. In the expression, we are going to have our hydrogen. It's a product, so it's on top. And we're going to have our hydroxide on top as well, because it's an expression of the product. That is all we have, nothing to put on the bottom. We are done. Finally, I want to take a look at one last one of a salt being dissolved. Taking a look here, again, we have a solid this time. This is also a pure substance. With it being a pure substance, just like before, we are going to ignore it and not use it. Instead, we're just going to be looking at our last pieces and putting them in. They're both products. So we'll have that lithium Keep the ion together so you know that that's an ion, not an atom. The 2 goes outside. And then we have the carbonate. And that is our final expression. So these are the way to write your expressions for your different things. Remember, pure substance, liquids and solids, we do not use. You only use gases and aqueous solutions. And yes, in the beginning here, these are all gases in that Haber process.